Now let us discuss about the chemical properties. The molecule of ethylene glycol contains two primary alcoholic groups. It exhibits the general chemical characteristics of primary alcohols twice over. However, in most of the reactions, both these groups are not equally reactive. One hydroxyl group reacts completely before the other. One participates in the reaction. In general, this resembles a primary alcohol in all chemical reactions. The first type of chemical property is of replacement of acidic hydrogen. The hydrogen atom of the OH group is replaced by electropositive metals like sodium step by step with evolution of the hydrogen gas. The hydrogen present in ethylene glycol attached to this oxygen here is known as the acidic hydrogen. On addition of sodium metal at 323 Kelvin results in the formation of monosodium glycolate. On further addition of sodium metal at 433 Kelvin results in the formation of disodium glycolate. Reaction with organic and inorganic acids to form ethers. In all the reactions we have discussed above, protonation of the OH group is followed by nucleophilic attack by the anion of the acid. For example, ethylene glycol on hydrogenation in an addition of hydrogen halide. Here, the halide ion replaces the hydrogen group here, and thus the OH group is removed by forming water as a side product. Furthermore, ethylene glycol reacts with hydrogen chloride gas as follows. Ethylene glycol on addition of hydrochloric acid at 433 Kelvin removes the water molecule from here, thus forming ethylene chlorohydrin. Ethylene chlorohydrin on addition of hydrochloric acid at 473 Kelvin furthermore removes this hydrogen molecule and forms water as a side product, and thus the main product formed is ethylene dichloride. On heating with nitric acid in presence of a catalytic amount of concentrated sulfuric acid, the ethylene glycol forms ethylene dinitrate, which is an explosive liquid at higher temperatures, and thus water is also formed as a side product. Ethylene glycol reacts with organic acids such as acetic acid, that is CH3COOH, in the presence of mineral acid, forming glycol mono and diacetate. The three-dimensional structure of ethylene glycol is shown as follows, which on hydrogenation produces glycol monoacetate and also glycol diacetate. Now let us discuss about the reaction of ethylene glycol with dicarboxylic acids. Acetyl chloride, acetic anhydride also forms the same product with ethylene glycol. Both the glycols and dicarboxylic acid, being molecules with two functional groups, react forming condensation polymers. Thus with terephthalic acid, ethylene glycol forms the polymer terylene, which is also known as dacron or terene. This product thus formed is extensively used as a synthetic fiber. Further on, let us study about the reactions with phosphorus halides. Ethylene glycol forms ethylene chlorohydrin and ethylene dichloride with ether. Similarly, PbR3, also known as phosphorus tribromide, forms mono and dibromide. With Pi3, it forms ethylene diode, which being unstable decomposes to form ethylene. For example, let us take glycol, ethylene glycol. Here, on addition with PCl5 or PCl3, we obtain ethylene chlorohydrin. On further reaction, we obtain ethylene dichloride. Instead of PCl5, if we take PBr3, the same product is obtained, but instead of chlorine, we'll be having bromine here. Similarly, this is the intermediate product of ethylene glycol on addition of PCl3. On removal of iodine, we would obtain a double bond between the carbon atoms, and thus is known as ethylene diiodide, which is very unstable product. Ethylene glycol undergoes dehydration, that is removal of hydrogen, under different conditions to form different products. When heated alone up to 773 Kelvin, it forms ethylene oxide or ethylene epoxide. Epoxide is nothing but a closed ring structure with oxygen at the center. This is an intramolecular reaction in which a water molecule is eliminated from the two OH groups. That is, this OH and this hydrogen is removed, thus forming water as a side product, and this oxygen needs another bond, so it comes and joins with the carbon here. When heated with anhydrous zinc chloride, ethylene glycol forms acetaldehyde. Thus, this is a beta elimination reaction. The product shown here is an intermediate of the reaction between ethylene glycol in the formation of acetaldehyde. In the second step, this hydrogen migrates from the OH group to the CH2 group. This hydrogen removes a double bond here, thus forming CH3. So the oxygen forms a double bond with this carbon. Intermolecular dehydration. When heated with concentrated phosphoric acid, ethylene glycol eliminates a molecule of water, forming diethylene glycol. This involves a nucleophilic attack by the OH group of one molecule to displace the protonated OH group of another molecule. If we see here, ethylene glycol on addition of H3PO4 or on decomposition will form this product diethylene glycol. This hydrogen and this OH group is removed to form water as a side product, and the oxygen bond links with this carbon atom here. Concentrated sulfuric acid, being more powerful acid and dehydrating agent, removes two molecules of water, forming dioxin. Previously, we have seen only one removal of one water molecule. Here in this ethylene glycol, this OH group is removed, and further on this OH group is also removed. That is why sulfuric acid is used. Thus we obtain two rings as follows. This oxygen bonds with this carbon, and similarly this oxygen bonds with this carbon, thus forming a dioxin. Ethylene glycol contains two primary alcohol groups. Hence, number of oxidation products are possible. That solely depends on the nature of oxidizing agent, the quantity of the oxidizing agent used, whether one or both the primary alcoholic groups are oxidized. Acidified potassium dichromate or potassium permanganate is very powerful oxidizing agent. Hence, they are very much capable of cleaving the C single bond C bond, forming formic acid. The CH2OH, that is ethylene glycol, on addition of 3 moles of oxygen results in the formation of formic acid and thus water as side product. This is a 3-dimensional structure of ethylene glycol. Periodic acid is a specific reagent to bring about such a C single bond C cleavage by oxidation. This undergoes cleavage of carbon-carbon bond forming two molecules of aldehyde, and on further reaction we will be resulting as formic acid and water. Both these reactions involve the formation of cyclic diester with the reagent as intermediate. Dilute nitric acid or alkaline KMnO4, also known as potassium permanganate, oxidizes ethylene glycol to the following oxidation products. The first step involves the formation of aldehyde by the oxidation of one CH2OH group. The second step may involve oxidation of other CH2OH group to aldehyde. The further oxidation of CHO group to COOH group, ultimately oxalic acid is formed. Oxidation reactions. Nothing but glycol on addition of oxygen results in the formation of glycolic aldehydes. On further addition of oxygen, we would obtain glyoxyl and glycolic acid. This on further oxidation produces glyoxylic acid and oxalic acid.